Okay, so I start by greeting Sundar and wishing him long life and longer mathematics, and thanks to Vijay for the kind invitation to speak. Okay, so what we are going to do is discuss some kind of motivation and introduction to large deviations. What I am going to do is I will start with a simple problem. Imagine that there are n particles. This is called a spin system. Each particle can have two states, either +1 or -1. Therefore, if you look at the whole bunch of n particles, each of them can be in any one of the two states. So, possible configurations of these n particles are given by set of all sequences of +1s and -1s of length n. Okay. Each such thing telling what is the state of the particle. Okay. Elements of this space I shall denote by sigma. Now comes an interesting concept. Whenever the particles have a certain configuration sigma, they possess a certain energy. Okay. That we shall denote by Hn sigma. Beta greater than 0 is a fixed number. What is that number? I will tell you in a minute, and why I would take a number beta at all. This e to the power of minus beta Hn sigma. So, if you take a configuration sigma, there is this number Hn sigma. I look at e to the minus beta Hn sigma. This is called the Gibbs factor for the configuration sigma. And if you look at the sum of all these Gibbs factors, it is called the partition function. Okay. So, what are these things going to do and why are we interested in this? This is the kind of thing that appears in the statistical mechanics of spin systems. Since I am not a physicist, the best I could do is to quote a physicist. If a system in equilibrium can be in one of k states, 1, 2, 3 up to k, and energies are E1, E2, Ek, then the probability that the system is in state I is proportional to that number, e to the power of minus energy divided by certain number. Okay. And there are two things there, kappa and T. Kappa is called Boltzmann constant and T is temperature, but we are not bothered with that. You can think of that 1 by kappa T as beta. Okay. So, basically you have e to the power of minus beta Ei. So, probability that it is in the state I is proportional to e to the minus beta times energy. So, proportionality will tell you if you sum all those things, that is the constant with which you have to divide these numbers in order to get a probability. So, this probability equals 1 by q times that, and if we have an observable quantity f, okay, on the particles, then the expected value of this observable quantity is precisely the expectation, as you know in probability, value multiplied by probability added up. Okay. This fundamental law is the summit of statistical mechanics. That is what Feynman says, and according to him, entire subject is either slide down from the summit as the principle is applied to various cases. So, you take different systems and apply this principle and try to see the consequences, or the climb up where the fundamental law, namely the one that I have stated just now, is derived from other concepts, okay, which will possibly clarify the meaning of temperature and the meaning of thermal equilibrium. What we are going to do is we shall look at the first one, okay. We shall accept this and apply it in our case. Why is the partition function?
Called a function.
Yeah.
Why is it called
Why is it called a function? I don't know, that seems to be the standard terminology. Function of temperature. Right. So it is simply the normalization constant. So as Kalyan says, it is perhaps function of the temperature, and yeah, in fact that does come into picture a little later. Object of interest is 1 by n log Zn. Okay. You would wonder how suddenly this log came into picture. Okay. So if you look at log Zn, okay, suppose you differentiated that, okay, with respect to beta, then log of f is f prime by f. Therefore, if you differentiated log of this, then you will get this in the denominator, and the numerator will be summation Hn sigma with a negative sign e to the power of minus beta Hn sigma. In other words, a careful observation would reveal that this is nothing but the average of all the energies with a negative sign. Incidentally, the negative sign there reveals the fact that the lower energy is what is preferred. Okay. All right. So the object of interest as far as we are concerned is to calculate this limit, okay, 1 by n log Zn. All right. Now what is that? It is simply, I have written log Zn there, summation sigma belonging to configuration space e to the power of minus beta Hn, but I have introduced a 1 by 2 to the n there. Okay. By equivalently, I did not mean that both answers are same. If you evaluate this, you would know what that is. Okay. I have divided by 2 to the power of n. So the 1 on the top is nothing but 1 in the bottom plus 1 by n log 2 to the n, okay, to compensate for the division by 2 to the n, but that is of course log 2, it does not depend on n. Therefore, if you can evaluate this, you would know the first one. Okay. But I will rewrite the simple thing which is a summation in a rather complicated way. 1 by n log integral over the configuration space e to the power of minus beta Hn sigma d lambda, where lambda is the uniform distribution on sigma n. By that I simply mean it is the probability that gives probability 1 by 2 to the n for each configuration. Therefore, integrating with respect to that probability simply means taking the average, nothing more. That is the previous one. Okay. So the problem mentioned is same as evaluating this limit. Okay. Now there is a problem here. Each of these quantities that we are calculating depend on the configuration space sigma n, and the configuration space keeps on changing as the number of particles increases. It is better if we had one place where all this drama takes place. Therefore, with that in mind, I will write the above thing. So remember what we have, integrating e to the power of minus beta Hn sigma with respect to uniform probability. So look at that sigma n, define a map to the real line with the configuration sigma, I forgot that Hn sigma by n, okay, not Hn by n. So with the configuration sigma, associate the number Hn sigma by n. Uniform probability on sigma n as a consequence is carried over to the real line, that is the induced measure. You can call push forward or whatever. So basically mu n of any subset of real line is take the inverse image, count the number of points, that is it. Okay. So integrating my function on this is same as integrating the function e to the minus n beta x with respect to the induced measure mu n. Okay. So, here earlier I had u to the minus beta h n sigma, you can write it as u to the minus n beta into h n sigma by n. Okay? And since I have used the map h n sigma by n, okay, the induced measure, the earlier integral is precisely integrating u to the minus n beta x with respect to mu n. Okay. Now, I will make a wishful thinking. Mu n is an unknown measure, and Professor Nadkarni was talking about Lebesgue measure, Cantor and so on. So, pretending that we know Lebesgue measure better, suppose d mu n is like e to the power of minus n I x dx, suppose. Okay? Of course, there are two things you will ask. What do you mean it is like this? Okay? When do you say that something is like something else? That is number one. Is this correct? Okay? These are the two things, but let us see. That is only a thought process. So, if d mu n is like that, then look at the top there, I can replace d mu n by e to the power of minus n I x dx on the top. Okay? So, that will be e to the power of minus I see. E to the power of minus n beta x I x o. There is again another printing mistake. There is no more mu n there. Okay? That is simply dx. So, please keep in mind d mu n x is e to the minus n I x dx. So, that mu n there should not be, it is dx. Okay. E to the power of minus n beta x plus I x dx. Okay. Now, the question arises. You said d mu n is like e to the minus n I x. Okay? In other words, we are pretending as if this measure is decreasing towards the point 0 at an exponential rate, right? That is what it is going to say, e to the power of minus n I x, if I assume I is positive, etc. That means the measure. So, you might ask, are there reasons to believe that this is so? Well, as of now, I have not said anything about the energies h n sigma, right? So, as of now, there is no reason to believe, but however, there are some practical considerations. H n is the energy of this system in the configuration sigma. Therefore, h n by n is in some sense in the configuration sigma per particle. As the number of particles increases, then per particle energy should become smaller and smaller, otherwise you will be stuck with infinite energies. So, that is one reason. But then the question is, okay, the numbers are near 0, why exponential factor? Okay. Of course, you can say that generally anything in probability, right, anything anywhere that goes to 0 at a very fast exponential rate. Okay. Of course, in mathematics that does not happen, 1 by n goes to 0, but not exponential, but generally in practice that is what happens. However, another thing is the number of configurations is 2 to the power of n. Okay. As n increases, what happens to that? The number of configurations increases at an exponential rate. Therefore, if you believe that there is a average energy over all configurations, then each of these numbers must be going to 0 at an exponential rate. Okay. In any case, this is only a belief, right? So, let us see where this will take us. So, the problem is to evaluate e to the power of minus n beta x I x dx. Okay, as I told you that mu n is a printing mistake. Okay. So, what is that? 1 by n log, of course, that is log of this whole to the 1 by n, right? Beautiful. Why is that beautiful? Because forget about limit and log, look at that complicated factor. It is e to the power of minus beta x plus I x raised to the nth power. Integrate, take the nth root. That is what you did. Therefore, this is nothing but the LP norm. Okay. Therefore, I now make, my interest is as n tends to infinity, right? And somehow I have read somewhere that the LP norm goes to the sup norm as p goes to infinity. Okay. So, hopefully, this is the second wishful thinking. This one, these LP norms converge to the L infinity norm, that is the sup norm. Okay. But of course, if you believe it is actually the sup norm, forget about L infinity and all those things. Okay. The answer is then limit over n log. Okay. You have to look at log of the sup norm of the integrand. Okay. E to the power of minus beta x plus ix. Okay. You have to take the sup norm of that. That is where the LP norms converge. Hopefully, this is all a hope. Therefore, log remains as it is, sup of that exponential. Okay. But that is very interesting. Earlier, when I had log Zn, I was absolutely helpless, right? Log of sum of exponential factors. There was no way for me to get rid of the sum between log and exponential. But now I am absolutely well placed. Supremum of the exponentials and then take log. You can cancel log and exponential, right? Because supremum of exponentials is exponential of the supremum. You can just take that. So, you will get sup of minus beta x plus ix. And of course, that is minus infimum of beta x plus ix. Okay. That is it. So, we have neither performed any integration, nor have we done anything. Answer to our question is minus infimum of beta x plus ix. Okay. So, the whole question is about the thought process that led to this. What is the meaning of the first wish? What was the first wish? D mu n is like e to the power of minus n ix dx for some nice function I. And what is the meaning of that at all? We do not even know the meaning. Okay, all right. If you give a meaning to that, the next question is, does it hold? And then, is the second wish true? I simply said that the LP norms converge to L infinity norm, right? Okay. But we are giving a meaning now to d mu n being like e to the power of minus n ix dx. So, with that meaning, we have to now see whether the LP norms or whatever we are thinking about, they convert to the L infinity norm. Okay. So, these are the questions. If we settle these questions, then we are in good shape. The first one, the meaning of the first wish is absolutely large deviation principle, no more and no less. And the meaning of the second one, second one means 2 question marks, that is the third line there. Okay. So, the second wish, that is precisely Varadan's integral lemma, no more and no less. And the question, which is the second line there, with marks, that depends on our number set and sigma. Okay. So, the question is, number 1, what do you mean by saying d mu n is like n ix dx? Okay, here is the thing. So, here is the definition. Suppose for each n greater than or equal to 1, you have a probability mu n on the real line. Okay. The sequence mu n satisfies large deviation principle if there is a function I with values in the interval 0 to infinity, the value infinity is allowed and not identically infinity, such that for every Borel set, if you look at lim sup of 1 by n log mu n, it should be smaller than minus infimum of I over B, well not B but actually B closure. Lim sup should be smaller than that, lim min should be bigger than minus infimum of Ix over this thing. Now, B closure is a larger set than B interior, so that infimum is smaller, infimum over B closure is smaller and minus of the infimum is a larger quantity. So, the larger quantity appears at that side and smaller quantity appears on this side. So, basically if you forget about all lim min, lim sup etc. so on, okay, look at this line lim sup is equal to that. So, what is it saying? Forget about lim. 1 by n log mu n of b is like that. Okay. That is mu n of b is like e to the power of minus n of whatever that quantity. Okay. That is precisely the thing. So, this is what makes this precise the meaning of d mu n is like e to the power of minus n I x dx. Okay. This is the precise meaning. Okay. Of course, this does not say that you are eligible to replace d mu n by e to the minus n I x dx in any case. Okay. This is the meaning. Okay. I said for every Borel set something should happen. Okay. 1 by n mu n of b should be like e to the power of minus n of something infimum of I x over b and so on, or b closure. But then that is too difficult. Okay. Because too many Borel sets you can't do this. So, it is not necessary to verify that. It is enough to verify for open sets. There are two lines there which should be satisfied. The top line if you verify for open sets, bottom line if you verify for closed sets, okay, that is good enough. Then it follows that this holds for every Borel set. Okay. And now we have a precise definition of log deviation principle. As you see, there is nothing about the real line that one used. You can look at any Polish space, that means a complete separable metric space, okay, and you can have a sequence of probabilities mu n on this Polish space. They satisfy log deviation principle if that inequality holds. Okay. There is a second condition in the inequality in that definition which I have not read, and that appears in proving things and so on. Okay. If you are not proving anything, it does not appear. Okay. That is a technical condition, which is the so called level set. If you take any real number a, look at all points where your function I takes the value less than or equal to a. That should be a closed set. Okay. That is a technical condition, and this is usually known as lower semi-continuous. Okay. Okay. For several reasons it appears. Okay. So, I said the definition makes sense for any Polish space. So, what is a good example of a Polish space? You take the real line, you take the collection of all probabilities on the real line, that is a Polish space, right. You can define weak convergence on it, namely a sequence of probabilities mu n converges to mu if for every bounded continuous function integral f d mu n converges to integral f d mu. Then the collection of all probabilities on the real line is itself a complete separable metric space. Okay. So, you can take that, you can talk about a sequence of probabilities on that. Okay. All right. But anyway, so this is the Donsker-Vardan definition of log deviations. So, the first question is, did people talk about it earlier? Yes, they talked about it in a limited way. Kramer talked about it in 1938. This is in connection with insurance problems, and so you can say that the profound mathematical theory of log deviations started from insurance problems. Yeah, whenever I talk about Kramer, I am very fond of saying he started in chemistry. He wrote about half a dozen papers. Then one of the reasons influenced him to take up mathematics. Then he wrote about a dozen papers in analytic number theory, and then he had trouble finding job. Actuarial companies were ready to create a professor post and give him. He switched to probability and then did that fundamental work. Okay. So, how did that appear in insurance problems? You see, if I am running an insurance firm, I will be interested in knowing how many claims will be there, you see, because I need to pay the claims to the customers, and what will be the average claim. Okay. Then I will be well settled, well prepared. But however, at the same time, I have to make sure that my company is not ruined. So, even though the average claim may be 100 rupees, imagine that tomorrow there is a claim for 1 million rupees, then my company is ruined. If you tell me that later on there will be several claims of only 10 rupees, that does not help me. Therefore, it is important to know not only the average claim, but what are the chances of deviating from the average by a large amount, okay? Which is same as asking what are the chances of my company not being ruined. Okay? So, that is the motivation with which we started, and then there were works by Chernoff and Sanov again, and Bahadur and Rangarao and Seturaman and so on. These are all in connection with statistical testing. Okay? So, they did it, but in a limited way. First of all, there was no definition of large deviations. They were only trying to find out, as I told you, I will give an illustration, probability of deviating from the average value, okay, by an amount. How do you estimate it? That is all. Okay? But they did not realize what exactly is the definition. They did not realize what is the power of large deviations, what you can achieve with it. Okay? And they did not realize that the ubiquity of the large deviations, that things, large deviations are present in all convergence problems. Okay? So, these are three things, but however, so let me get back and tell you what exactly was Kramer doing in a simple illustration. So, consider n tosses of a fair coin. Yeah?
Didn't Sanov prove a theorem for
multinomial thing.
Yes, Sanov proved one of the earliest theorems with some kind of a definition of the range function.
Correct, yeah, but not, yes, correct. So, he again I think gave simply only the estimates, but he did not have for every Borel set this kind of thing and so on, I think, yeah. And yeah, basically RD and so on, correct. Sanov did do that pretty close, right. Okay. So, suppose you toss a fair coin, there are 2 to the power of n outcomes, right. Each toss can be heads or tails, probability half and half. So, each of the 2 to the power of n outcomes are likely. Now, look at the proportion of heads. Okay. It could be 0 by n or 1 by n, etc., n by n, but of course, these are not equally likely. Okay. The chances that the proportion of heads is k by n is given by n choose k 2 to the minus n, right. There are n choose k outcomes out of the 2 to the n outcomes with k heads. Okay. Denote this probability by mu n. Therefore, mu n is a probability on the unit interval. It is concentrated on these n plus 1 points, and the probability of this k by n is n choose k 2 to the minus n. Strong law of large numbers tells you, or if you want, you can say ergodic theorem. Okay. So, whatever, this proportion converges to half almost everywhere. Okay. So, mu n converges to point mass at half. Okay. Now, the question is the following: find the chances of deviating from half by an amount larger than 0.05. Okay. So, this proportion converges to half almost surely. Of course, when I wrote that thing there, I said look at the tossing a coin n times. Since I am talking about limits, I have to look at the infinite product space of tossing the coin infinitely many times, okay, and look at the first n tosses and then calculate the proportion and look at these distributions and so on. Now, you can talk about the limits. Okay. So, what are the chances that mu n, that the proportion is outside the interval 0.45 to 0.55, okay. That should go to 0, right, because mu n is converging to point mass at half. Okay. So, how small is this? That is definitely going to 0, but how small is this? And here is the answer. Look at the following function ix as log 2. When x equal to half, it is half log half plus half log half, that will be log half. Okay. If you add log 2, you have 0. So, it comes to 0. Then again it starts increasing. Okay. It is symmetric, it increases to log 2. Okay. The answer is the following: mu n of this set 0.45 to 0.55 complement is like e to the power of minus n alpha. What is alpha? Alpha is the infimum of ix over this interval, okay, over the set of our interest. But our set is 0.45 to 0.55 complement, okay, and the function is decreasing here, increasing here, symmetric. Therefore, if you take the infimum here, it is same as taking the value at 0.55. Okay. From half to 1, it is increasing. So, if you look at 0.55 above that, the minimum value is at 0.55. Okay. So, that probability is like e to the minus n alpha. Okay. What do you mean by it is like e to the minus n alpha? Is there a precise theorem? Yes, this is the precise theorem. Limit over n 1 by n log mu n of your set converges to minus alpha. That is the precise theorem. Okay. So, roughly speaking, for large values of n, 1 by n log mu n is minus alpha. So, that is it. Okay. So, this is what they were doing, not necessarily with coin tossing, but with more general things. Okay. What about the second wish? Okay. Second wish is when I said LP norms converge to L infinity norm. Okay. Yes, that is precisely this Varadhan's lemma. If mu n obeys large deviation principle with rate function I, and if you have a real bounded continuous function f, then 1 by n log e to the minus n f x d mu n x converges to minus infimum of f x plus I x. Okay. So, in other words, you do not have to pretend that mu n is like e to the minus n I x, put it there and then pretend LP norms are going to L infinity norm, etc. So, this theorem tells you all that is valid, okay, for any bounded continuous function. And of course, in our case my function f x is beta x, okay, that is not bounded. Okay. So, f x is beta x, oh, not minus beta x. But if all our measures probabilities are concentrated on a bounded interval, that is okay, fine. You can say any continuous function, because the entire drama, if all the mu n's are concentrated on a bounded interval, then the entire drama takes place on a bounded interval. So, you can apply that theorem for any continuous function. Okay. Now, so I have explained what is meant by saying that d mu n is like e to the minus n I x dx, and I have stated what exactly is the analog of LP norms converging to L infinity norm. Now comes the basic question, okay, fine, the meaning of the first wish is explained, but does it hold? Okay. Now, how do you know our mu n obeys LDP? It all depends on the numbers h and sigma. Okay. So, are we going to give criteria? Now, this is where once again, in a sense, probability takes over. Okay. We are not going to give criteria. Okay. Let me give an example. Look at the series 1 plus half plus 1/3 plus 1/4, etc. That series diverges, right? Look at the series 1 minus half plus 1/3 minus 1/4, etc. Alternative, that converges. You can ask, for what assignment of signs does the series converge? Okay? I have the same numbers, I have changed the signs. Okay. Once it is diverging, once it is converging. So, you can ask. There is really no useful answer. Okay. However, the right question is there any typical behavior? You know, we are not interested. Okay. Just as the government is not interested how much money I earn, it is only interested what proportion of people earn certain amount of money and so on. It is interested overall. So, in the same way, what is the typical behavior? Okay. Is there any such thing at all? The answer is yes. If signs are assigned at random, typical behavior is convergence. It typically converges. Okay. What do you mean by saying signs are assigned at random? Okay, here is one way to make up our mind. Take any number x in the interval 0 to 1. Look at the binary expansion. Okay. All right, some numbers have two binary expansions. All right, make up your mind. Either to take non-terminating expansion or terminating expansion, whatever, doesn't matter. Okay, it makes no difference. Now, here is the way. Nth sign is plus or minus according to the nth binary digit is 0 or 1. Okay, assign signs in that fashion. All right. So, take any number x that determines one way of assigning signs for these numbers. Now, if you do this, then typical behavior is the convergence. That is, look at the set of all numbers x in the interval 0 to 1 such that for the assignment of signs determined by x, that series converges. Okay. That set has Lebesgue measure 1. So, almost surely it converges. So, it is a question of typical behavior rather than behavior in each individual case. Okay. And so, here we take the same attitude. Try to put a good probability on your sequences of numbers and explain typical behavior if any. Okay. That they satisfy large deviation principle for almost surely choice of your numbers. Right. And here I am now talking about putting a probability on the sequences HNs. Okay. The question arises, did you lose touch with reality? Okay. What is this you are talking about? You said that some spin system, some +1 -1 and some statistical mechanics nonsense and so on, and then now you say put probabilities, okay, on the sequences. Okay. Are you trying to sort out any specific problem or only mathematics? Well, this is actually a model suggested by Anderson long ago explaining magnetism and so on. So, you think that atoms are placed at lattice points, okay. There is an interaction and so on and so forth, you solve all sorts of problems. That is nice as far as magnetic materials are concerned. But however, in the late 60s, there was much interest in what they called dilute magnetic alloys. That is, you take a non-magnetic host and in that there is a magnetic dust particles present. Okay. So, the entire thing is non-magnetic and there are some magnetic materials present. Now, this alloy exhibits magnetic behavior. So, explain that. Now, the physicist Anderson proposed that now there is no point in thinking that these atoms are located at lattice points and there is an interaction between neighbors and so on. Okay. If you want to talk about neighbors, it is much more complicated. You should know exactly how these magnetic movements are present in the non-magnetic host. Okay. That is impossible. And also, it is impossible to write down interactions. Okay. Even if somehow you bring in some geometry and take every point, take a certain ball, look at all particles in that ball and so on, and bring a certain geometry and want to take interactions between neighbors, okay, it is rather complicated. So, what is suggested was the following: you should now take Hamiltonians to be random, okay, and see whether there is any typical behavior that emerges, okay, out of this. That was the proposal, okay, and I think maybe early 70s or something he got Nobel Prize for that thing. Okay. So, here is one example. This is called random energy model by Derrida. For each n, look at the random variables Hn sigma. So, now Hn sigma are not numbers, they are random variables. They are independent, identically distributed Gaussian, mean 0 and variance n. Okay. So, they are random variables defined in a probability space. So, if you fix one point omega in your probability space, you have got a system of numbers H and sigma. Okay. You can show that typical behavior is existence of the limit. Typical behavior is that this mu n, remember when we had numbers, okay, then we had a probability on real line. Okay. If you have numbers H and sigma, then we look at the following probability on the real line, which puts mass 1 by 2 to the power of n at the point H n sigma by n, okay, H n by n. There are 2 to the power of n points, some of them may be same, does not matter, okay, repeat, H n sigma by n, 2 to the power of n points as sigma varies in the configuration space. So, for all those points we have given each 1 by 2, that is the measure mu n. Okay. So, the theorem is this: for almost every sample point, these configurations have the property that mu n satisfies a certain large deviation principle, and therefore, you can get hold of the function I, and once you get hold of the function I, it is simply a matter of calculating supremum or infimum, whatever, you can get hold of the limit. Okay. It does happen here. And there is another model, the so called Sherrington-Kirkpatrick model. In fact, that was my interest. I wanted to see, but I have not succeeded. Okay. So, here what happens? H n sigma is 1 by root n summation j I j sigma I sigma j, where j I j are independent standard Gaussian variables. Okay. This is also random. Now, okay, you might get worried what the hell is going on here. Above I said variance n, and bottom I am somehow saying J's are standard Gaussian variance 1, but do not worry. How many Gaussian things are here? You see, in this thing there are n into n minus 1 by 2 Gaussian things, okay, and each has variance 1. Therefore, the total variance, because they are all independent, okay, J's are independent, therefore, that variance is n into n minus 1 by 2. Therefore, if you look at the variance of this, okay, 1 by root n square comes when you calculate the variance of alpha x, alpha square variance of x. Therefore, 1 by n times n into n minus 1 by 2, it is also of the order of n. Okay. So, there is nothing silly going on there. Okay. Look at H n sigma to be that. This is called the SK model, and here also that limit 1 by n log z n exists, okay, but not by the method I have described to introduce LDP. Okay. Not that there is any large deviation principle, possibly there is, that is what I wanted to see, I have not been. Okay. So, this is one example, and I said ubiquity of large deviations. There are several situations where this LDP holds in connection with Brownian motion. For example, Rajiv talked about Brownian motion in the morning. If you look at Brownian motion on the unit interval, it is nothing but a probability on C01, space of all real valued continuous functions on the unit interval. There is a probability mu. Okay. There is a natural map from C01 to C01. Okay. If you look at any function, look at 1 by root n times that function. Okay. That induces a probability, a transformation of the Brownian probability. Denote this by mu n. Okay. So, mu 1 is the standard Brownian probability on C01, some probability, it does not matter what it is. Okay. And from C01 to C01 I define a map. Any function xt simply goes to the multiple 1 by root n times that function xt. Okay. This root is something that bothers probabilists all the time anyway. So, that induces a probability, call this mu n. This sequence mu n satisfies a large deviation principle. Okay. One of the interesting things, and the trivial analog of that is the following. Look at just a unit interval, let mu 1 denote the Lebesgue measure on the unit interval. Okay. Define the map from unit interval to the unit interval, x going to x by n. Okay. Look at the induced map, call it mu n. It is concentrated on the interval 0 to 1 by n, right? Mu n obeys large deviation principle, that is very trivial, okay? But the Brownian thing is not trivial. Similarly, there are several other instances where the large deviation principle holds, but I shall now mention one instance, okay, where the large deviation principle holds. Okay. Now, a random matrix. Okay. It is an n by n matrix. How is this n by n matrix made of? I take IID random variables, okay, which are centered Gaussian with variance 1 by 2n. I put them above the diagonal, and I take centered Gaussian with variance 1 by n, I put on the diagonal. All these random variables n into n plus 1 by 2 are independent. Okay. And what do I do below the diagonal? I make it a symmetric matrix. Okay. Therefore, it is automatically determined what you should put below the diagonal. So, this is a symmetric matrix. Now, I have carefully stated on diagonal, above diagonal and so on, but this is all unnecessary. You can, there are more general theorems, but however, this is how Wigner originally had, and the reason he took that thing is to make a nice quadratic form and so on. You can calculate explicitly the density of certain random variables I am now going to describe. Otherwise, you can ignore all this. You can take IID random variables above the diagonal, okay, and some other IID random variables on the diagonal, etc. But let us ignore that. Okay. Look at the random spectral distribution. Okay. What is that? So, I have a matrix whose entries are random variables. Therefore, if I fix a point omega in my sample space, I have a matrix of numbers. This is a symmetric matrix. So, calculate the eigenvalues and put mass 1 by n at each eigenvalue. That is the probability mu n. Okay. So, ln is 1 by n summation delta lambda I. Okay. So, these are the n eigenvalues. I shall put mass 1 by n. This is called the spectral distribution. It is known almost surely ln converges to the semicircle law. What is that? Look at the interval minus root 2 to plus root 2. With that as diameter, you draw a semicircle, okay, upper half. Think of it as a density function. Naturally, if you want a probability density function, you have to normalize. Okay, that is precisely what is happening there. D sigma x is 1 by pi square root of 2 minus x square. That square root of 2 minus x square is the function f x, which I said semicircle with minus root 2 to plus root 2 as the diameter. Okay, that 1 by pi is normalization to make the total area wall. Indicator mod x less than or equal to root 2 simply tells you that my function is 0 outside the interval, minus root 2 to plus root 2. Okay, so that is a nice density function, and d sigma x, sigma is a probability. What is the theorem? Almost surely ln converges to this. Remember, ln is a probability on the real line. Okay, it sits on the n eigenvalues of your matrix. All right. It is random because our matrix is random. If you fix a point omega, you got a matrix of numbers. Now, for almost every sample point omega, if you look at the sequence of probabilities ln, it converges to sigma. Okay. In what sense? For every bounded continuous function, integral f d ln converges to integral f d sigma. Okay. Or if you do not want to look at it that way, you can simply say ln of any interval converges to sigma of that interval. Okay. And in this case, it does not matter. When there are discontinuities, there are problems, but these two definitions are equivalent. Now, remember I said that the definition of large deviations makes sense for any Polish space. One example of Polish space is the collection of probabilities on R itself, PR. Okay. Now, here we have a beautiful situation. Okay. What is that beautiful situation? I have my n by n matrix. Okay. If I fix a point omega, this is a matrix of numbers that gave rise to eigenvalues, that gave rise to a probability on the real line. Therefore, every sample point gave rise to a probability on the real line. Okay. So, I have a map which sends sample point to a probability. Therefore, this induces a probability on the collection of probabilities, right? Because for every sample point omega, I have an element in PR, namely the spectral distribution of matrix obtained by fixing that omega. So, this map from your probability space to PR induces its distribution. Therefore, you have a probability on PR. You denote this probability by mu n. Okay? So, mu n is nothing but distribution of ln. Okay? ln is not a real valued random variable, but it is a PR valued random variable. Therefore, you have a distribution on PR. You have a sequence of probabilities on PR now. Okay? The beauty is this sequence of probabilities satisfies a large deviation principle. Okay? And what is that? So, I have to tell you the function I. Okay? Where are our probabilities? On PR. Therefore, my function should be on PR. Okay? So, take any nu in PR. Define this function half integral x square d nu x makes sense. Okay? X square is positive. Minus integral log mod x minus y d nu x d nu y makes sense. Okay? The only thing is you might wonder whether the first one could be infinity and the second one could be infinity too. Then this doesn't make sense, this minus that. Okay. You can show that the whole thing is finite. Okay. Minus 1/4 log 2 minus 3 by 8. Okay. So, whatever it is, it doesn't make any difference. It is not the nature of the function. That is what we are going to look at it now. ln satisfies LDP with this rate function. Okay. Now, why did I mention this special example with rate n square? Remember, when I said large deviation principle, I did not want to give the most general definition, which makes no sense. I simply said 1 by n log mu n of b should have certain property. Okay. Now, here 1 by n square log mu n of u is greater than or equal to minus I u. Lim sup of 1 by n square log mu n of f is less than or equal to minus I f. Exactly the same thing as I gave in the definition. Okay. But instead of 1 by n log, you have 1 by n square. Okay. So, in other words, it satisfies large deviation principle with rate function I, and rate is n square. Okay. And roughly speaking, it is n square because n square uncertainties are determining this. Okay. Look at how many random variables I have. Okay. To determine ln, I have n into n plus 1 by 2 random variables, right. So, forget about all this algebra of the order of n square. So, there are n square random variables which are determining this. So, that uncertainty enters into this rate. So, this is now you can see nothing special about n or n square. You can state Vardhan's lemma with changed rate and so on, okay, 1 by n square, that is also correct. And now, there is a nice review article, Large Deviations and Stochastic Calculus for Large Random Matrices by Alice Gione in Probability Surveys. It connects evaluation of certain spherical integrals, large deviations and non-commutative probability. Okay. And in the spherical integrals, essentially you talk about integrating exponentials of certain functions defined on, let us say, space of unitary matrices. You integrate with respect to the Haar measure on the space of unitary matrices. Okay. Evaluating such integrals, and apparently one of those is Harishchandra integral and so on, and I have not been able to understand anything. I should try again. So, those spherical integrals, they are connected with the large deviations, and naturally when I talked about random matrices, non-commutative probability enters into picture. Okay. Because as Voiculescu proved, the reason you get that semicircular law in that Wigner's theorem is because these matrices are becoming, in a sense, not only independent random variables are put and so on, they are becoming freely independent. Okay. They obey that principle. That is why it is related to the free probability. Okay. So, I will stop with this one. I have not stated any theorem, but only the idea is to give the precise definitions of large deviations and how it arises. But of course, historically it did not arise from the problem I have mentioned. But if you are starting with this problem, this is a nice way to bring in large deviations. Thank you.
Chatterjee has very recently extended this last deviation result of Benarus and Guinea for non-Gaussian matrix elements.
Oh, I see. I didn't know that. Okay. Yeah.
Just appeared in the KP volume.
In?
Honor of KP.
Oh, I see. Okay.
Very recently.
Ha ha ha.
Chatterjee and Gordon has contributed an article
Right.
extending Benarus's result to certain class of
Yeah.
non-Gaussian.
Right. Right.
And second comment is that this n square last deviation principle for the matrices apparently has found practical use in your mobile telephones.
I didn't know that either. Okay.
The engineers use it to design various kinds of telephonic
I see.
systems.
Alice June, do they get any money? See, thank you. Yeah. Thank you.